happiest lectures of the year with the Bach Prize award, because this is a chance to welcome back a graduate of the department who's gone off to do wonderful things. And this year's awardee is Meredith McGregor, because she was not just a graduate student, but she was an undergraduate thesis with Ito. And then she came here for a PhD, and she won a bunch of different teaching accolades with her teaching, and graduated in 2017 with a really, I think, a landmark piece of work on the disks with Alma. She then went to be a NSF postdoctoral fellow and Carnegie postdoctoral fellow at DTM, and finished there in 2020 and moved to join the faculty at the University of Colorado in January 2020. Very good timing. Got to meet your colleagues in person before the curtain fell. But Meredith has really distinguished herself since her thesis with her continued work in the formation and habitability of planetary systems. I don't want to steal her thunder, but I mean, to me, the pictures from Alma of these protoplanetary disks, I think, are really one of the highlight in just astronomical imaging in the last 10 years. I'm not going to vote on the science impact, but you know, I think aside from M87, the M87 folks might have a jog in the race, but I really think that the pictures from Alma on the protoplanetary disks are just completely evocative, and I'm sure we'll see a bunch of those in the talk. And she's also made her mark in the impacts of stellar activity on the habitability of planets, and I think we'll hear some about that as well. So let me thank Meredith for coming today. We have a certificate and a check. And so thank you.
And I have the formal handshake.
With that, let's take it away.
Okay, put this over here. Great, it's fun to be back. I realize this is the first time I've been back here since I graduated, so it's like been a minute. Especially after I spent a whole solid 10 years here. It's like a simultaneously weird deja vu feeling, but like also it's different, but it's still kind of the same, so it's been an interesting 24 hours. So I gave this talk, this like pretty vague and grandiose title that we're going to discuss how to form a habitable planet. And the reason I did that is because my research group at CU Boulder is pretty diverse in what we work on. So we use essentially any telescope that I can convince someone to give me access to try and understand all pieces of planetary systems. So really trying to draw connections between these planetary disks and the actual planets that form from them and the star that's in the middle that's irradiating everything. And I always show this talk because a lot of the wonderful science that I get to show is now done by my amazing research group. So here's all of the names of all of my students and our like Zoom COVID picture, because since I started in January 2020, most of my students started working with me on Zoom, and we had really fantastic Zoom group meetings. And that is the picture we have. So at the moment, I have 3 full-time grad students, one who's doing some side projects with me, a postdoc, 5 current undergrads, and then 3 undergrads who've actually come, done honors thesis, and left all during the pandemic. And so you'll see their names in the bottom of the slides because a lot of the things that I get to show are things that they've worked on as part of their projects. Okay, so I always start with an overview of how we form planetary systems. Here, that's maybe not as necessary because there's a lot of expertise here, but we'll go through the same thing. So we think that planetary systems form from giant molecular clouds, where pieces of that cloud get overdense and they collapse, and we form a new star, and that star is surrounded by this disk of dust and gas, what we call a protoplanetary disk. This is the phase where there's enough material to actually form new planetary systems. Lasts for somewhere on the order of 1 to 10 million years, very large error bar on that. And then most of that material is cleared away, and we're left with a main sequence star, any planets that formed during this earlier phase of evolution, and then what we call a debris disk, which is really kind of the remnant material left over. So if you'd like compare those 2 populations of disks, on the left, these are all the D-sharp images of forming protoplanetary disks. So these are all pre-main sequence stars. They have a lot of gas in them, which is primordial material. Only time that we actually have enough material in these disks to form giant planets, certainly. And so I always like to call protoplanetary just sort of the reservoirs of planet formation. Whereas on the right, now these are all my images of debris disks. These are main sequence stars. They do actually have gas in them at mostly lower levels. And the picture we have is that actually these are sort of like our Kuiper belt, where you have asteroids and comets that are now colliding and grinding. And as they collide, they also outgas ice. And so we're seeing outgassed CO from these cometary collisions. There's certainly not enough material to form giant planets here. Maybe we could form terrestrial planets. And so I like to call debris disks sort of the fossil record of planet formation, because what's left, the structure of these disks, is really like shaped by the planet formation process that happened earlier. And we can observe all of these disks across the entire electromagnetic spectrum. So here are 4 images, all of the same debris disk. This is AUMIC, one of a few debris disks known around an M-type star. The top image is taken with sphere, so this is where we're actually seeing scattered light in the near IR off of tiny micron-sized dust grains. And then if we move to the bottom panels, this is Herschel, Alma, and the VLA, so moving out from 70 microns to a centimeter in wavelength, where you're actually seeing thermal emission now from larger dust grains. So we're tracing different emission mechanisms as we move through different wavelengths, and you're also tracing different grain sizes, and that lets you get this really multiply resolved picture of planet formation, right? Because we can spatially resolve these systems as a function of different grain sizes. But of course, a lot of the images that I get to show you are from Alma, because Alma has completely revolutionized how we think about planet formation. So here's Alma, which we're all intimately familiar with. But really, Alma has amazing angular resolution and sensitivity, which allows us to take this gallery of debris disks, which is pre-Alma. None of these images are from Alma. And some things look interesting, and a lot of things look like blobs. And then turn them into the now Alma view, where these are all the exact same disks. And you can see that things that are blobs now have eccentricities and gaps and structure. And we have a completely different view of the systems that we're trying to study. OK, so that's the disk introduction. But I framed this talk as like how to form a habitable planet. So what does that mean? We astronomers really like to make the simplest definition of habitability, which is this, right? We define habitability based upon if I have an Earth-like planet with an Earth-like atmosphere, where can I place that planet in its orbit that it will have the appropriate surface temperature to allow for liquid water on the surface. So if I move the planet a little bit too close, it's going to get too hot. All the water is going to boil off. If I move the planet a little bit too far away, everything freezes. And you get this nice observational test, right? We can go out, we can measure planetary properties and see where they are in their orbits. And we can say, maybe they're habitable, maybe they're not. But there were a lot of descriptors that I put into that, right? I said it's an Earth-like planet with an Earth-like atmosphere. And really, habitability is a much more complicated picture, right? Just moving an orbit around tells us some information, but it doesn't really give us a complete picture of habitability. And if we want to answer that question, we need to get into a lot more details. If I look at our planetary system, technically there are 3 planets in the solar system that have at some point been in that habitable zone. I would get Venus, Earth, and Mars, and only one of those has humans on it sitting in a colloquium talk. So clearly something's different between these, right? Venus is a little bit too close in. So it dried out the surface of the planet, which made it not have plate tectonics. And so there's no carbon cycle on Venus. There's no CO2 cycle to actually pull CO2 out of the atmosphere. The atmosphere of the planet is 96% CO2, and it's a horrible place. And Mars is a little bit too small. So Mars cooled completely, has a solid core. And as a result, it lost its magnetic field, which allowed the solar wind to completely strip away the atmosphere of the planet. So there's a lot of other factors that I'd put up if I wanted to tackle the question of is something habitable or not. And where I like to try and do my work is using different parts of planetary systems to tackle some of these things that we can't get at by just looking at, say, transit light curves of exoplanets. So I'm going to start with highlighting 2 different factors here. The first is do other planetary systems have outer giant planets? Which seems like a really basic question to ask, but we don't actually have the statistics to be able to answer this right now. Why do we even care? So in our Earth's history, where we formed would not have had any water built into the planet because we're within the snow line of the solar system, which is actually out in the asteroid belt. Which means that all of Earth's water has to have been delivered to it. And so you need Jupiter to suddenly go on this motion in the outer solar system and stir things up in order to deliver water. This is our typical exoplanet plot, which shows the mass of exoplanets as a function of period. And they're color-coded by discovery method. There's really like 3 main ways we discover exoplanets. We can look for transits. We're actually trying to look for the planet crossing in front of the star. We can look for radial velocities, where we're seeing the star and the planet actually tug on the star and seeing the shift, the Doppler shift in the stellar lines. Or in some cases, we can actually block out the light from the star and take a direct image of the exoplanet itself. And all of these have some significant biases, which you can see when you look at this plot, right? If we're looking for transits in RV, we want to see multiple transits or multiple wobbles. So you're biased towards looking for things on short orbits and for looking for things that are quite massive. So you end up with this huge pileup of planets on like really short orbits. And with RVs, you end up with this giant population of like close-in giant planets. But we're completely missing the area that overlaps with where our giant planets are in the solar system, right? We're not detecting any Uranus or Neptune or Saturn analogs, and a lot of that is just, you know, I'm not going to sit here for 140 years and look for transits. We haven't even known about exoplanets that long. So that means we need some other way to try and get a handle on the outer parts of planetary systems. And where my interest lies is actually trying to use the structure of these evolved disks to then actually model that structure, understand the dynamics of it, and say something about whether there could be giant planets that are shaping these disks. Okay, so if you imagine having a planet sitting on the inner edge of an outer debris disk, it's going to gravitationally perturb that dust, and you might expect to see structure there, right? Things like eccentricities or warps or resonant clumping. And we do see this in some systems, right? The left here is Beta Pictoris, which has a directly imaged exoplanet in it. And the exoplanet is on a tilted orbit relative to the plane of the disk. And so there's actually a warp in the inner part of the disk caused by that planet. And even in our own Kuiper belt, the Kuiper belt that we define as the classical Kuiper belt, which is the red and the blue points here, is actually very narrow. And it's narrow because it's confined between orbital resonances with Neptune. So as the solar system had its initial dynamical instability and everything moved outwards, Neptune basically snowplowed all of this material into these resonances that it's been maintained in. So it's not crazy that we might expect to go look at other debris disks, see structure, and then model that, and be able to say something about planetary systems. So let's look at some examples of debris disks. What do they look like? So this first disk is Fomalhaut. Fomalhaut is one of the most famous debris disks. It was one of the first ones imaged. It looks a little like the Eye of Sauron in this Hubble image. And Fomalhaut is interesting because it's eccentric. So the diamond there is showing the center of the disk, and the star is then labeled by the white symbol. And they're offset. It's enough of an eccentric disk that you can visibly see the offset between the center of the disk and the actual stellar position. And it had a tentative directly imaged planet, which then is now maybe a dust clump because it's not present in the current Hubble images. But it was an intriguing system if there was really a planet orbiting on the inner edge causing this eccentricity. So back in my PhD work, we made the first sort of millimeter map of this, which was a mosaic image made with Alma. And so I've overlaid that on top. The pink here is now the disk center, so you can still visibly see that offset between the center of the disk and the star. And then there's the planet question mark. And we now have new data from Alma, which one of my grad students is working on analyzing right now. So the disk is visibly eccentric, right? It's clearly eccentric. And what you notice is that actually it's brighter at the apocenter side of the disk than the pericenter side of the disk. So when I play with a super elongated elliptical orbit here, planets on elliptical orbits actually move slower at apocenter, farther from the star. This is Keplerian dynamics. And they move faster when they come closer to the star. And so if you imagine a lot of comets that are all in eccentric orbits, they're going to move slower at the apocenter side, faster at pericenter, and you would predict that there should be a surface density difference in the disk, that you'd actually see the surface density be higher at apocenter than at pericenter because now you're probing the material from the disk. What's interesting is that now with these new images, we can get even better resolution. So we're down to having roughly 1 AU resolution. And depending upon the planetary orbit that's interior to that disk, if there really is a planet shaping it, you actually don't just predict that there should be this difference in surface density, but that you should see an azimuthal change in the width of the disk. Because depending upon the planetary orbit, like in our solar system, you basically pinch the orbits at pericenter with Neptune. A lot of these eccentric Kuiper belt objects all have the same pericenter position. And then they extend their orbits in apocenter, so you actually end up seeing this like difference in the width of the disk as you go out. So what I've done here is taken that Alma image, but I'm only showing the pericenter and the apocenter sides and like flashing between the two of them. And you can actually see that with this, there's a significant difference between the width and the surface density profile between apocenter and pericenter. So for the first time, we're actually like really probing down to the resolution we need to consider those dynamics. Okay, so there's also other structures we might see in disks that are shaped by planets. One possibility is that planets might carve out gaps in a disk, like we see in those D-sharp images. So this disk was studied again with Hubble, and what was notable about it is that it's actually 2 times as extended on the right side as it is on the left. So it's like twice as extended on the right as on the left side, and that was thought to be because maybe this disk is interacting with the interstellar medium, that it's actually like colliding with a dense clump of ISM gas, and it's like dragging grains out in some kind of ram pressure stripping. So we imaged it with Alma to try and see where the larger particles were. Like where are those millimeter-sized grains? So now on the right is the Alma image, and then it's overlaid as contours on the left. And what was surprising is it looks nothing like the Hubble image at all. In fact, there's no evidence of this extension in the Alma image, and instead, it looks quite blobby. Now, I stare at pictures of disks all the time, but not everybody does, so we get my donut primer. So if you imagine the left disk is totally face on, it has a 0-degree inclination. If I pick any line of sight through that donut, I'm going to see the same amount of material. It's the same thickness of donut. Now, if I take the donut and I incline it, so it's edge on to your line of sight, inclination of 90 degrees. If I pick a line of sight through the center, I'm going to see donut and then hole and then more donut. But if I pick a line of sight on like the far right, it's just going to be donut all the way down. So in an optically thin disk, you should see this, what we call onsci, or limb brightening, basically, that comes from having more material where there's not a hole. And if we see then like these sort of brightening on the edges of a disk, that indicates that there's a gap in the middle of it when viewed edge on. So I can go back to this blobby looking disk. The center here is actually the star, and then there's 2 onsci on either side of the star with a gap in between them. And this is then best fit by having a model where there's an inner disk, a cleared gap, and then an outer disk. Okay. So that's nice because we can then try and say, imagine that there's a planet sitting in this disk. Like, could it explain this gap that we see? So we can then actually use the properties of that gap, the radius and the depth and the width, to actually place a direct constraint on the planet mass, which is what's at the top here. And then we can run dynamical n-body simulations with rebound to actually see, does that work? So this is showing a 0.16 Jupiter mass planet inserted into a disk that's about the exact same properties as we see with Alma, and then run for 1 million years. And it does, in fact, open a gap. You can play around with it a little more if you allow the eccentricity to increase. So this has a slight eccentricity, which allows you to open up a bigger gap with a slightly smaller planet. But it seems to sort of make consistent sense. Okay. Now, I showed you those 2 examples for a reason, because most recently, we've been looking at this disk, which is just truly bizarre and seems to have both. So this is HD 53143, and it's a sun-like star that's about 1 billion years old. So it's like a young solar analog. And this is the Hubble image. I would almost squint at this and you probably can't necessarily tell that there's actually a disk in that image. It looks terrible. There's basically like two clumping of material on the like lower left and the upper right. And this was thought to maybe be like a face-on disk where we're seeing like resonant clumps. So we imaged it with ALMA. It doesn't look like that at all. This is the ALMA data now overlaid on top of the HST data. And the center point is the star again. So this disk is extremely eccentric. It's about twice as eccentric as Fomalhaut is. The star is quite offset from the center of the disk. And we see that same brightening at the apocenter side of the disk. We then imaged it again with HST, better STIS coronographic image. And this is now the HST image, again overlaid. So we've improved. The catch is that it still doesn't match the ALMA data. If you fit the ALMA data, allowing for a vertical thickness to the disk, you get that the disk should be extremely thin. But if you fit the Hubble data, it wants to be really puffy. So it actually has like a significant vertical height to it, which means that the large grains and the small grains are actually in different places. There's some confined plane with the larger millimeter grains, and then this elevated population of small grains in this considerably eccentric disk. Okay, but it gets even more fun. So this is the actual model fit to the data, where we fit an eccentric disk model to this disk. So it's showing the data on the left, and then the model at full resolution, and then the model image like the data, and then the residuals on the far right. And those residuals are up to 6 sigma. So they're significant. The dashed line to guide your eye is actually the inner and the outer radius of that outer disk. So if we were fitting the outer disk well, we shouldn't see anything in that dashed region, which we don't. So we're like net overall fitting that outer disk, but there's a lot of emission coming from inside of that we cannot explain through an eccentric disk model. So it's not immediately clear what's going on. The best guess that makes some dynamical sense is actually that there's an inner disk in this system as well, and that what we're seeing in those two contours is basically the onside of an inclined inner disk, that same like limb brightening phenomena. If that's true, that means that the outer disk is eccentric, and then there's an inner disk that's actually inclined relative to the outer disk, and then there's a gap in between them. So this was the helpful artist's impression that NRAO put together for our press release at the AAS meeting last summer, in that there's now this outer disk, and then this inclined inner disk, and then the hypothetical undetected planet. Good news is that we will get new ALMA data on this system soon, provided that ALMA doesn't have any more shutdowns, and then we'll be able to actually go back to the system with that 1 AU resolution that we used for Fomalhaut to get a really high resolution view, which would be good enough to actually resolve that inner disk if there is an inner disk. So if we take all of the disks that we have seen and image with ALMA, it seems like structure is pretty much ubiquitous. Like we see it in almost all of these disks. There's a lot of rings and gaps. And I can wildly extrapolate and infer planet masses for all of those rings and gaps and plot them down on the same planet mass exoplanet diagram. So this is the same thing. Its mass is a function of the same major axis. All of the gray points are those known exoplanets. The black points are the known solar system planets, and all of the colored symbols are the planets that are inferred by just modeling the gaps in structure in these disks. And many of these may not actually be planets, but they do very nicely fill in this space where we have these giant planets that we have in our solar system, and we don't know whether they exist in other exoplanetary systems. And I'm particularly excited, a number of people here involved in this. There's a large program happening on ALMA right now to actually image a large sample of debris disks with high resolution and look for structure in debris disks to do this even more. Now, what else can we say that's interesting about disks and exoplanets? So my one undergraduate student did his honors thesis where he was actually trying to look at whether disks are inclined relative to their star. So you might expect that nothing crazy has happened. Your stellar axis is straight up and down, and your disk would be perpendicular, and everything would make sense. There's a large question about what forms these sort of hot Jupiters, these giant planets that are close to their star, and one option is having dynamical instabilities that actually move them inwards, that they form further out and then get scattered in. And if that was the case, then it might end up leaving an imprint on the remnant disk by basically like sending things out of alignment. People had tried to do this previously with pretty small samples and largely found that things were aligned, and so everything made sense. My undergrad went back and used the test data to actually measure the stellar inclination angles, and then we took all of the resolved debris disks with ALMA and fit inclinations to them, and this is what we get. So it's just inclination as a function of stellar inclination. Everything that's in blue and along that line is like mutual inclinations are the same, and the red points that are now off are things that have significant offsets in their inclination, where there's clear evidence that the disk is not aligned with the star anymore. Okay. And of course, I would be very remiss if I just said everything was planets, because clearly it might not be. There's lots of other things that can produce structure in disks that we need to understand in order to really conclusively say that anything is planets. So this is a project I've been working on with Anne-Marie Madigan, who developed a model of an inclination instability for the outer solar system. Basically a way to explain the orbits of outer solar system bodies without needing to add planet 9, where if you have a large enough population of stuff, you can actually have mutual self-gravity, and it excites this instability, which you can see progressing through these model panels at the top. So basically, you end up exciting like a wing, where the orbits from the self-gravity get perturbed slightly out of the plane of the disk, and then they get perturbed the other direction, and they sort of like flap to this mutually inflated disk over time. And I show this because, I mean, that's cool, but also because we see debris disks that have very similar structure. So this is a real HST image of HD 61005 called the Moth, because it has this wing-like structure to it. And so this is just an example of another way that we could produce structures that we'd like to say might be planets, but just through the self-gravity of bodies in the outer parts of these solar systems. Okay, so I'm going to take an abrupt turn into the center part of planetary systems, because in the middle of all these disks and all of those lovely ALMA images I showed you, there is a bright point source, which is the star. Why do we care about stars so much? So stars, including our sun, flare. They send out bursts of high energy radiation. They also send out charged particles, what we call coronal mass ejections, or CMEs. And they travel out into space and they hit your planet's magnetosphere and can come into the atmosphere and actually dissociate molecules in the atmosphere. So they can split apart things like ozone and water. And on Earth, this is what produces the aurora, right? It's coronal mass ejections from the sun, actually ionizing parts of Earth's atmosphere, dissociating these molecules, and giving us beautiful northern lights. On many of our exoplanet systems, the star in the middle is not a sun-like star, it's an M-type star, and M stars are much more active. They send out bursts and flares that are thousands of times more energetic than anything we've ever seen from our sun. And so it starts to kind of throw into some question this idea of habitability, because you might be getting irradiated by your star. So in order to really like tackle this, we need to think about stars in a multi-wavelength way, because stars emit across the entire electromagnetic spectrum. And in fact, different wavelengths of light are actually tracing different emission processes and even different places in a flare loop. So the left is sort of the cartoon picture of a flare, right, where we have magnetic field lines that are actually threading through the photosphere of the star. As the surface convects, those foot points move around, and that twists the field lines. Eventually, they twist up, and they snap and reconnect. It's what's called a reconnection event, and we get this like nice loop-like structure. There's electrons and charged particles that are actually accelerated around the top of the loop. We'd expect to see synchrotron emission that's traced by, say, millimeter and UV light. And then heating is actually propagated down the loop back into the photosphere of the star and heats at those foot points and produces thermal black body emission that we see in, say, like the near infrared and the optical. This is just our sun, where we can actually resolve flare structures. And this is a tiny wavelength range from 130 angstroms to 1600. But you can see this flare loop looks completely different, even across that small wavelength range. Okay, so how did I end up working on stars? Because of our nearest stellar neighbor, Proxima Centauri. So Proxima is an M-star. It's at 1.3 parsecs. It has 3 exoplanets now known orbiting around it. And the one that everybody's very excited about is Proxima b, because it's a roughly Earth-mass planet, and it's in that habitable zone. It's the right distance from the star to allow it to have liquid water if it's an Earth-mass planet. So a group went and took a deep Alma image of the system to try and see whether there was any dust. Because we have a multiple planet system around this nearby star, we might expect there to be remnant Kuiper belts in this system as well, and so they went to try and look for these disks. So the left image is the sort of published image from that paper. They used about 13 hours of Alma time. So they pointed at this star for 13 hours and then took all the data and averaged it together. And what you get is a point source in the middle that is bright. It's like 340 microjanskis, which is significantly above what the stellar photosphere should be. The photosphere should be about 70 microjanskis if it's just an M photosphere. If you look at just the first 12 hours of data, you get the middle panel, which now looks quite different. There is actually nothing detected above 3 sigma in that middle image. And if you look at just the last hour, you get the right panel, where now there's an even brighter point source with a flux of roughly a millijansky. So something's clearly varying in time. Now, Alma actually has a 1-second integration time. So instead of looking at total observations, we can actually look at each of those integrations separately. And if you do that, you get this, which is now the time, and it's about 6 minutes of data. There's only emission from the star for about 2 minutes. The rest of the time, the star is actually not detected at all. And we see this series of sort of small hiccups and then this giant burst where the star brightens by a factor of almost 1,000, and then it decays away to nothing, and we have no more emission from the star. So that clearly indicates that there's not a disk in this system, because disks don't do that. But it was the first time that we'd actually detected millimeter flaring emission from these M-type stars, which was exciting and maybe a new way to try and understand stars and their activity levels. But in order to do that, we needed to actually place that in some kind of context, because I can't just say, yes, stars flare in the millimeter, but I have no idea what that correlates to or what's coming from, right? So we undertook this large campaign to actually go back to Proxima, but now with the millimeter and a range of wavelengths. So we had 40 hours of time where I tried to convince every telescope to point at Proxima at the same time. It was fun. We had Alma, several ground-based telescopes doing optical photometry and spectroscopy, TESS in space, so we actually coordinate the TESS window when TESS was looking at Proxima. And then we used Hubble and Swift to cover the UV, and then Swift and Chandra to cover the X-ray. So everything from the radio all the way through the X-ray. And all of these were executed completely simultaneously. So we just pointed at Proxima for the exact same time. And when you do that, it turns out that you get really interesting data sets. So this is an example of the first flare that we pulled out of the survey. So this is stepping through wavelength here on the left, with Alma, the longest at the top, going through TESS, and then DuPont looking at the H-alpha and helium-1 lines, and then Hubble with continuum and silicon-4 emission. And the right is now just zooming in on the Hubble and the Alma data together. And there's a lot of really interesting things to take away from this plot. So the flare is enormous in the Alma and Hubble. It's the largest flare we've ever seen from Proxima with Hubble. It brightens by a factor of almost 15,000 in the Hubble light curve, and it brightens by a factor of more than 1,000 in the Alma light curve. Each of these points is a 1-second integration. So the entire event lasts 8 seconds. So it bursts and has that 14,000 times brightening in about 4 seconds before decaying away. The optical light is very different. It's very small, actually. The emission increase in the optical is tiny. And there's actually a significant delay between when we see the peak in the Hubble and the Alma data and when we see the peak in the optical. So there's actually a gap in time. They don't occur simultaneously. But the ALMA and the Hubble data are like strikingly locked together. It makes, I think, physical sense, because if they're both coming from synchrotron emission, then we would expect to see this. And if the optical is actually coming from, say, black body heating that's propagating down, then it's maybe not surprising that there is this delay and difference between the emission at those wavelengths. What's interesting, because we typically observe flares in the optical, and then we wildly extrapolate to say now we know the UV emission because it's the UV that we actually want to know when we think about atmospheric stripping and photochemistry. Optical light doesn't do that. So we scale optical flares all the time into the UV, and if they aren't actually linked, then that makes me feel a little uncomfortable about that. And if the millimeter turns out to actually be a better tracer, that would be very exciting, because it's a lot easier to do millimeter observations. And in fact, all of these CMB surveys are going to suddenly be observing tons and tons of millimeter flares. They already are publishing millimeter flares out of SPT, and we could get a lot of data very quickly with millimeter flux measurements of nearby stars. Okay, so just to highlight that optical is really different, this is what we call a flare frequency distribution, which is number of flares as a function of energy and amplitude. So really big flares are all the way over here on the right. They're rare. And really tiny flares are all the way on the left, which occur pretty much daily from Proxima. And these are all of the flares that were detected from Proxima in the entire test time that it looked at the star. And the green line is that flare I just showed you that brightened by 15,000 times with Hubble. So in the optical, 75% of the flares detected from Proxima are brighter than that flare. And in fact, we would estimate that basically we'd see that flare once a day if the optical and the UV are connected. We can also use ALMA to say some more interesting things about the emission mechanisms of the star, because with ALMA we get a spectral bandpass where we observe across a range of frequencies, so we can actually then calculate a spectral index, so how the flux varies as a function of frequency. And we can try and recreate a lower limit on the linear polarization by taking the XX and YY polarizations. So this is 3 different flares. The left panel is a previous flare from Proxima. This is a flare from AUMIC in the middle. And then this is that new Proxima flare on the right. The top is just showing that light curve again. So flux is a function of time. Here's the spectral index and then the linear polarization. And we see some very clear changes. As the flare happens, the spectral index changes from being like a Rayleigh-Jeans black body tail to noticeably negative and then recovers. And there's an indication that there's actually a change in the polarization of the star. And they all look pretty similar, so we're starting to build up a sample where they all appear to have pretty comparable properties. And this is consistent with a picture of either having synchrotron or gyrosynchrotron emission. We would expect to see this sort of spectral index change and this linear polarization if we're really seeing this sort of emission mechanism. Now we've been like continuing to comb through the data from that survey. So this is a paper that my postdoc put out earlier, which is actually the first ALMA and Xray flare. So this is Chandra data that we got at the same time as ALMA. So the right curve is on the far left showing Chandra, LCOGT, and ALMA. It's a very different flare because it's actually quite small in its like total energy. It's about similar to like an X-class flare on the sun, which is the largest flares that our sun puts out, but like small for an M dwarf. And now, because it's actually comparable to the sun, we can start looking at it in kind of the landscape of solar flares. So this is showing here these sort of typical Gödel-Benz relationships. We plot X-ray luminosity as a function of radial luminosity. And it's interesting because the ALMA data in quiescence, like when the star isn't flaring, seems to be roughly consistent. But when the star flares, it like really jumps up in the flaring emission. So it seems like there's some kind of overproduction of millimeter emission happening during these events compared to like solar flares. And I don't actually have an explanation for that, except that we are starting to get the data that we can look at that. What else can we do? So now, this is like brand new and like not published at all, so take that what it is, but my postdoc has been working on JWST observations. Turns out that when you try and take emission transmission spectra of your M dwarf exoplanets, you still have the M dwarf in the middle. and it can flare in the middle of your transmission spectroscopy. So the top light curve is the actual initial light curve from JWST, and you can see this peak up right as it's going into the transit. This is a model where we've actually tried to take out the transit light curve, because the exoplanet people would really like to just take out that flare and see what happens in the exoplanet atmosphere, which you can't do if there's this flare sitting on top. So the hope is that if we understand the flare, we can better model it and remove it. But then also the JWST data on the flare is astounding to me, because we detect every spectral line ever. So this is H alpha. We have all the Paschen lines down to Paschen epsilon. This is a bracket beta line. We have helium. And suddenly we can see all of these emission lines, how they vary as a function of time and wavelength. And we can actually use these to inform these radiative transfer models and actually say things about the magnetic field of the star at the time of the event, how many particles were accelerated, the energies that were released during that. M-dwarfs aren't the only ones that actually flare at millimeter wavelengths. So this is just a highlight from a paper looking at Epsilon Eridani on the left, which is a sun-like star, where we reanalyzed the ALMA data and found several flares happen from the star. And this is actually HD 53143, that really crazy debris disk I showed you. Turns out it has a crazy star as well. So we observed that for 8 hours with ALMA. And the flux from the star changes dramatically in the middle, which we think is also due to a flare. The background here is actually TESS data, because it turned out that TESS was observing at the exact same time as ALMA by complete chance. So we can actually look at the optical light curve at the same time. And what's surprising is that for a billion-year-old sun-like star, it has an enormous amount of spot modulation. So much so that it really messed up the HST coronagraphic imaging, because the reference star was failing, because the star was actually changing color due to the spot modulation. So I think that there's lots of places to go from this. One thing I'm really excited about is thinking about what kind of new telescope we might want. And to me, the really interesting lever arm here is getting the multi-wavelength emission, but that's very hard right now. We have to try and coordinate 8 different telescopes, and it would be nice if we didn't have to do that. So I'm working on a new mission concept with JPL called SPEX, which is focused on looking at young stars to study young exoplanets, young disks, and young stellar activity. And it's meant to be a multi-band instrument with near IR optical and near UV and fast cadence, less than 30 seconds cadence, staring at all of these sources with all of those bands at the same time. So we don't have to try and make multi-wavelength light curves, we just get them. And then the next step is to connect this to an actual understanding of astrobiology, right? Because it's great to just understand stars, but we'd really like to think about how they alter atmospheres. So this is a project I've been working on with Laura Schaefer, also fellow alum here, where we are trying to actually model what these flares do to atmosphere chemistry, specifically looking at oxygen. Because oxygen is talked about a lot as a biosignature, since it's really tightly linked to the rise of life on Earth. We had no oxygen in the atmosphere, and then plants happened, and then we get oxygen. But you can actually basically produce a giant oxygen column density just by allowing these flares to propagate through the atmosphere, because they dissociate water, and then you can drive hydrogen escape in these young exoplanets. You lose the hydrogen, and you're just left with a ton of oxygen. And we are then also collaborating with a geneticist at the University of Minnesota to try and do this in a lab, where we're actually going to use a UV flash bulb to try and simulate UV flares in a lab and see what damage it might actually do to DNA. Okay, so I whirlwind tour of 2 of these things, but there's many other items on this list, right, that we'd like to get at and we can't. So what gives? 2 things that I think are of particularly key interest are trying to understand the water and volatile abundance, because you need to have water and volatiles to create life on a planet. So how do we get at that? Well, disks are complicated places. I like to show this figure and then say, we're not going to talk about all of it because it's deeply complicated. It's showing a debris disk on the right and a protoplanetary disk on the left. And different wavelengths of light are tracing different temperatures, so we're seeing different parts of disk with different telescopes. These young disks are flared, right? So we're seeing different depths into the disk. And so trying to actually understand the chemistry of disks is complicated, and there are certain things that we're completely missing. right now because we don't actually have the right tracers that we can access from the ground. So I've been working on another mission concept as the deputy PI called FIRST, which is the Far Infrared Spectroscopic Survey Telescope, which is designed to do high resolution spectroscopy in the far IR with the goal of really like getting at planet formation chemistry. And why is that interesting and important? So one point here is that we don't actually have a great understanding of the masses of planet-forming disks, which is a pretty fundamental property. I just showed you all this stuff about planet formation, and it makes it seem like this is really solved, but actually there's a lot of uncertainty. So these are all measurements done of TW Hydra, which is our like best studied protoplanetary disk, and they are all disk masses that use different tracers, and this is a logarithmic scale. So these mass-derived estimates span several orders of magnitude, which is problematic because you go from like having a decently sized disk to having a disk that's not going to form any giant planets at all, depending upon which tracer you've used. And maybe that's not super surprising because a lot of these use like dust masses and then try and scale that to a gas mass, or we use tracers like CO and then assume that we know the CO to H2 abundance and that CO isn't optically thick. We really want to actually measure the hydrogen reservoir. We can't do that. The thought to be best option is to use a molecule called HD, which is deuterated hydrogen. And unfortunately, HD only has transitions in the far IR at 56 and 112 microns. So it's been used in TW Hydra with Herschel, which is the top, but otherwise we have like 2 other disks that have ever had HD measurements of. And so one key here is that using HD, you really need to know the temperature of your material, so you really need to know its location in the disk, so you need to have really high spectral resolving power. So we've been targeting FIRST as this really exquisitely high resolution spectrograph to be able to do this. And the other really exciting thing to mention is water, because water is pretty fundamental to life. However, this is the landscape of water transitions that we can actually observe. So this is in energy bins, so hotter water at the bottom, colder at the top. The left is JWST, where basically there's a few water lines, but they're at really high temperatures, so they're not great for looking in disk environments. The right is Alma, where technically there are water lines, but we're looking through a water atmosphere, so this is tough. And then all of the transitions of water basically are in the far IR. So without a far IR telescope, we have no way to really trace water in star formation or planet formation or any environment. So like one big question is trying to look at the origin of water in disks and what are the abundances of disks where we don't actually have a good handle. And then we can also do this with comets. So we're even trying to look through comets in our own solar system, where the question is really like, where did Earth's water come from? And the way to get at that is to measure the ratio of deuterated water to normal water, so we call the D to H ratio. And we've done this a lot for asteroids, but not that much for comets. The comet population is pretty sparse, and we don't really have the sensitivities. So we're also trying to target doing comet science to really like measure the D to H ratios in a significant sample of comets. And the hope would be that if we combine all those things together with what we've done with Alma now, we can really put together a complete picture of planet formation. So with that, I will leave up my take-home slides, and I'm happy to take questions.
Okay, questions. I particularly want to encourage early career folks. Diana?
So do we have a good sense of how optically thick or thin the HD line is?
So the HD line should be optically thin, and it has been used pretty successfully in TW Hydra. The real like problem here and why there is still scatter is because of the temperature. So it's really sensitive to the temperature that you put into deriving a mass. And PAX only had a resolution of like 1,000 at 112 and like 1,500 at 56 microns, so not very good, which means that there's a lot of like uncertainty then in like deriving that mass, and so you end up with that, which is why we're trying to go for like higher spectral resolution to really robustly determine like where in the disk the emission is coming from, and thus the temperature, and thus the actual mass. You could also spatially resolve it, but we can't do that for $1 billion.
Please.
When you showed the really large flare in Proxima with in the different bands, so you had like a second cadence with like Alma, but then the optical had much larger bins in
Yep.
that time. Do you think that if you had higher cadence observations in the optical, that would change that picture at all, or do you think that that flatness is real? It's really that broad?
Bin of the data. So with tests, this is 2-minute cadence data. With a DuPont, it's bad because we're using a spectrograph, so we're actually like trying to detect an M-dwarf, and so you need to stare at it for like 8 minutes to get a decent spectrum. So there's multiple pieces on, like it's definitely a coarser spectrum. Even with that, the time delay is significant. They don't overlap. Like there's no overlap between the Alma flare and the test flare. And so even if like we were just not sampling it well enough, we should be able to have seen that, and we don't. So that offset is real. Definitely the energy could be higher in the optical because you're sampling an 8-second flare with a coarser cadence and adding a lot of noise in there, so you lower the significance of it. Not enough to make this agree, but there certainly could be a higher energy, which is why like fast cadence is really key for flare work, because you lose a lot when we look at these flares with these coarse observations.
Please.
On this flare, did you have overlapping Chandra data, and if so, did you detect it in the X-ray?
We did not.
That's what I was suspicious.
Yep. We only had a little bit of Chandra data, and so luck
Did
of
not
the draw.
Chandra did not overlap this time?
It didn't overlap with this.
Yeah.
The other, like this is the same campaign, just on a different day.
Right.
We did this over like 12 different days. And so this time Chandra overlapped, but it was a tiny flare. But like we still were able to get the overlap, just not unfortunately for that really big
Right.
one.
Thanks.
So the few flares that you showed were all main sequence stars. I wondered if you could say something more about the evolution of flaring over time, and whether or not there are any campaigns of younger stars to see how that might evolve.
Yeah, that's an excellent question. So in general, stellar activity declines as stars get older. So stars start off and they're spinning really rapidly and they're generally more magnetically active, and then there's some like tail off, right? Eventually they slow down and then they spin down and then their activity level goes down. So technically Proxima should not be so active. It definitely is much more active than you might expect in that simple picture. There have been some work done with Kepler to look at young stellar clusters in the like tens of million year age to try and like map this evolution, like how active, like how does this trend down? But I would say less than you might expect, which is why this particular mission we are specifically targeting young clusters, and by young I mean like 1 to 100 million years. At that time when like you would expect to be able to still detect like disk accretion and stellar activity, and also be looking at these exoplanets when they have puffed up atmospheres, with the goal on this to really like look at the early evolution and like sample 6-10 different clusters that span like 1 to 5, 10, 100 million years, so that you can really like try and study that.
There's an online question which we'll do quickly. Bob Wilson asks, can you use 13CO to measure mass to avoid problems with optical thickness?
So yes, they're like in this plot, I sort of like didn't go into this, but like every single one of these things is totally using a different tracer or some overlapping tracers. Some of them are 12CO, some of them are dust masses, some of them are 13CO, like C17, like name your isotopolog. And they certainly, like 13CO should be more optically thin than 12CO, but you still run into the problem that you're like using CO as a tracer for an underlying hydrogen reservoir, and we don't know the scaling between those things particularly well, so you still end up with some significant error.
Yeah.
So Meredith, when we look at lower mass, substellar objects flaring usually at lower frequencies, at gigahertz frequencies, we oftentimes find that these very short duration flares are 100% circularly polarized, not linearly polarized. And so I was wondering if with Alma you can extract robust circular polarization.
I would love to, because that very well could be, I mean, like that's just the lower limit by like using the XX and YY that you get for free with Alma. It says nothing about the cross products, and like it could very well just be circular polarization that we're detecting. Just have to actually convince, ooh, there goes the slides, convince Alma to let me stare at an unresolved point source with full polarization capabilities that may or may not flare, which is why I have not been able to get that data. But yes, that would be the best thing to do.
One last question from Melissa.
Sure. Thanks, Brian. Great. I'm just curious, all of these systems, the way you show them, look isolated, except for that one slide where you showed maybe there's some accretion. So I'm just curious, like, is there any interaction with binaries or with constantly accreting material or anything from outside that matters in this whole story?
In like the various disk sources.
Yeah.
Good question. I mean, most of these are at this point like isolated field stars, but they certainly didn't form that way. So it's a good question. There are some disks that have very weird structure that people like try and claim are stellar flybys. It's a tough one because you can never really like 100% prove that that's the case because you're seeing it now billions of years later. But maybe. Probably, right? I mean, stars form in dense environments, so I'm sure that plays a role. We just haven't.
All right, we're at the top of the half hour, so let's thank Meredith one more time.